So in this video, I will summarize the Biot-Savart law and how show an example question how we can apply the Biot-Savart law to find the B field for given distribution of current. So first, let me review the Biot-Savart law. So let's think about one-dimensional case. When you have line charge, let's say lambda, then whenever you have a charge distribution in the space, it will generate the E field. And as you learned in the Coulomb's law, we can express E field when you measure R. Then let's say you can measure ER electric field at this position. Then by the Coulomb's law and principle of superposition, you can find the E field using the line integral dl prime. Okay. However, when you have a line charge which is moving with a velocity v, okay, then the moving charge is considered current, electric current. So we can measure the current, and when you measure the current, you can pick a point here, R prime, then the current as measured at that red point will be lambda times v. So you are basically measuring, you select a point and you are measuring how many charges are passing through that point, which is definition of a current. So current will be lambda times v. And whenever you have a current in the space, it generates a B field. So B field, according to the Biot-Savart law, as measured at measurement point R, will become same line integral. Because we have to add up all the contribution of the small current pieces along the line, so you need a line integral. But the source of the B field is the current, not line charge lambda. So you should have here vector I at source position R prime. And now in the right hand side you have a vector and times vector should result in vector in the left hand side. So you need cross product. Right? So if you compare the equation between E field and B field, they are strikingly similar, okay? Which is very beautiful, I believe. And let's expand this idea into two-dimensional space. So if you have a set of charge distribution, can be defined by sigma, the surface or area charge density. And of course, this will generate the E field. I will not write down the E field here. But when it moves with a velocity, it generates a current. But before we measure the current, this area charge moving with a velocity v generate the current density. It's called surface current density K, which is sigma times v. And when you wanna measure the current of this two-dimensional charge movement, you have to, just like you pick a point, red point in the line charge case, you you have to look at the cross section of this paper, the sheet of charge, which is a line. And you set the line, let's say binding length of line L, capital L, and now you are looking at this line to count all the charges passing through that line. Okay, then you can measure the current. So the current will become line integral of the K along that red line L, capital L. Okay, and this current, surface current density K is a current, so it generates a B field as well, and the formula will be a similar structure. But now the source is the not line current, but the surface current density. So we have K here. And K can be in general, K can be different at different source position. And now we have K, and if you think about the unit, this is the area density, so you need a double integral here. Because the K, the surface current density K, exists on a surface. So we have to add up all the contribution from the small area pieces. So we need the K area integral here. And if you expand this idea to three-dimensional space, then you can imagine the three-dimensional charge distribution like a cloud or this type of cylinder. And when they move with a velocity v, then it generates a current. Right? And it is, by definition, it's current, movement of charge. And in this case, a movement of the volumetric charge distribution, we can define volume current density J. Okay, and when you want to measure the current, you can. It's the same concept. You have to set an area in the cross section, any arbitrary area from which you measure the current. Then current vector will become area integral over the your area A, the vector J. Okay, and more generally, this current density J exists like a three-dimensional vector field in the space. Okay, and that current density will generate a B field in the space, and that B field will have a very similar form as well. But now we have current density J here as a function of the source point R prime, and again this is a volumetric current density, so J exists everywhere, whereas the K, the surface current density, was existing only on a surface, okay, 2 dimension. But now we have 3 dimensions, so we need volume integral over all to add up the all the contribution from the current density vector field J. Okay. So this is a Biot-Savart law in the cases of a one-dimensional current distribution, two-dimensional current distribution, and three-dimensional current distribution. So I will show you one example. Let's think about, you can find many examples for the line current density, line current distribution in many textbooks and online. So here I will show you a little bit more difficult example where we have a two-dimensional current distribution. So let's think about simple geometry where we have infinitely long cylinder. Okay, it's infinitely long, and see here's the z-axis, x and y, Cartesian coordinate system, and radius is a, radius of the cylinder is a. And let's think, suppose all the current, surface current is flowing upward through the surface of the cylinder. So K is given, the surface current density K is K naught Z hat. Okay, the question is, this infinitely long cylinder will, of course, will generate the B field in the space, but now we want to find the B field specifically at the origin. So what will be the B field when we measure the B field at the origin of the coordinate system? Okay. And the question gave you the surface current density, so we will use Biot-Savart law. I mean, there are many different ways to solve this question, but I will use Biot-Savart law explicitly to show how to use it. So we will use this equation, this version of Biot-Savart law. Okay. And if you look at, so now you have a question and you have a formula, and you have to figure out, write down all the components in the right hand side. Okay, so this mu naught over 4 phi is just a constant. So you have to find what is r, what is r prime, what is k at that source position r prime, and what should be the integral range. Okay, you have to find one by one, and then you can plug in this into the equation, then do the math, then it will give you the answer. So in this specific question, the measurement position r is just origin, and r prime is the you can, when you write down the r prime, you can pick a specific position on the surface current. So we have a surface current along the cylindrical surface. You can think about small point here, and you can express this position vector r prime using any coordinate variables. But here we have a cylindrical symmetry, so let me express that using the cylindrical coordinate system variables, which is S prime, P prime, and height C prime. Okay, but this r prime is constrained on the given cylindrical surface, so it means that S prime is always A as a constant, and this point can be written down G prime, right? And then let's write down what is the source current K at that specific position. So in this simple question, fortunately it's constant, and you can write down this as a vector. Okay, this was given in the problem, the blue color. And dA, so we should do the area integral along this cylindrical surface. As you might learn in the vector calculus, you can think of a small piece of the patch along the cylindrical surface. So we want to find what is dA prime, and the vertical length of this patch will be dg prime, and the curved side will be sdp prime. Okay, S prime. But now it was s prime was equal to a, it's a constant, so it will be adp prime. So our integral will be, okay, and in order to cover all the surface of this infinitely long cylindrical surface, the integral range should be one circle from 0 to 2 pi for p prime, and for the z prime it will be negative infinite to infinite. Let's write down g prime first. So z prime from negative infinite to infinite, p prime from 0 to 2 pi. And then you can plug in all of these into the formula and then find the answer. Okay, so let me show you how to do that. So now we are specifically finding V field at 0, 0, 0. We will plug in all of these. So long, and dl prime was a dv prime, dg prime. Okay, and the numerator will be k first, cross product, and r minus r prime. So we know r and r prime, so we can write down r minus r prime, which is okay. And then the denominator is r minus r prime magnitude q. So it will be become this. So we can do this math. So let's do the cross product first. So when you do the cross product, 0, 0, K naught. So x component will become this one, minus this. And y component similar way. And z component will be 0. So if you plug in the result, and if you think about the integral of sine p prime and cosine p prime from 0 to 2 pi, this becomes 0. and the other integral this will not infinite, so the field will become 0. So if you think about the contribution of individual line, repeated long line current that compose the cylindrical surface, you can find out all the vector B field will be cancelled out at the origin point. So B field will become 0, right? But here I showed you how we can find that answer very explicitly using the Biot-Savart law of the two-dimensional case and the cross product. So to show the another example, let me solve the same question but half cylinder. Which means that it's the same question, but what if we have infinitely long half cylinder? So the surface current K is non-zero only for the angle phi from 0 to 5. Then the B field at the origin will be similar, but only different in the integral range. Not from 0 to 2 pi, but from 0 to 5. And the inside integral is the same. And you could expect that this will not be perfectly cancelled out to be 0. Because now we have an integral of the sine phi prime only from 0 to 5. So this will be two, and cosine phi result in 0. So the B field is not become 0. But we have another integral, the other integral to be done. G prime, okay? And for G prime integral, you can find the table of the integral, and we can do this. Or you can find YouTube if you want to find how we can find this definite integral from scratch. There are many videos on YouTube. But here we are only interested in the integral from negative infinite to infinite. Then this will, when you plug in infinite, this will become 1. And now if you plug in negative infinite, this will become -1. So the B field at the origin will be not 0. And vector 2, 0, 0. So we have only non-zero component in x-axis, x direction. Right? So it means that when you have this half cylinder, then infinity long, and when you measure the B field at the origin, it will have non-zero B field at the origin because this half cylinder, uh, the B field from this half cylinder is not perfectly cancelled out. Okay, so the X compound will survive. Okay.